Alright, so in this lecture I'm going to be talking about another approach for name entity recognition, and we are using machine reading comprehension framework. So I'm going to be explaining this paper in 2020. This is an example for nested entities that we cannot just say that model is with token, because we may have different entities for different spans. The task of name entity recognition is normally divided into nested NER and flat NER depending on whether name entities are nested or not. Models are usually separately developed for the two tasks, since sequence labeling models are only able to assign a single label to a particular token, which is unsuitable for nested NER, where a token may be assigned several labels. So in this paper, we propose a unified framework that is capable of handling both flat and nested NER tasks. And instead of treating a task of NER as a sequence labeling problem, they propose to formulate it as a machine reading comprehension task. For example, extracting entities with person label is formalized as extracting answer spans to the question which person is mentioned in the text. And this formulation naturally tackles the entity overlapping issue in nested NER. The extraction of two overlapping entities with different categories requires answering two independent questions. Additionally, since the query encodes informative prior knowledge, this strategy facilitates the process of entity extraction, leading to better performances for not only nested NER but flat NER. And you're familiar with machine reading comprehension, that for example, if you want to find a relation, the relation is just equal to a question. So we map from a relation to a question, and then we answer the question to find the entity which we know the answer, because it is one of the entity of the pair entity relation entity triple. And so this is we have input sequence, which we have the length of the sequence is n, and y is just a predefined list of all possible tag types. And we can consider it as machine reading comprehension. So we know the annotated entity start and end, we can represent it, and we obtain the triple, which is question, answer, and the context. So for each entity we have a question, so we're mapping the entities to questions. And the model backbone is typically, for example, we use BERT because we say the question and separate it with this separation token, and then the rest of that, and then passage X that we need to know as a context. But there are different ways for representation. For start index prediction, we just use a softmax of E, which is the representation of your BERT, and the start, the weight that you want to learn. The same thing for end. But we need start-end matching because there could be multiple entities of the same category. So this means that multiple start indexes could be predicted from start index prediction model, and multiple end indexes predicted from the end index prediction model. So by applying Rmax to each row of P start and P end, we will get the predicted indexes, and we can predict the probability that they should be matched. And we use cross entropy loss for both start and end, and we also need span. So there are 3 cross entropy loss because we know the gold answers.